So what we did in the first few lectures is formulate the first law, right? And if you remember how we did that, we wrote a statement of the first law that the internal energy is the sum of the energy flows into a system, the internal energy change. And then we spend most of our time essentially trying to write these things into state variables, right? So we spend a lot of time figuring out how you turn work terms into state variables. Turning du into changes of property of the system is usually much harder because it's system dependent. But we did that for one system in particular, for the ideal gas, where we could show that this was CVDT. But again, in general, turning this into state variables is quite hard. So in the most general form, you could write this as sum I yi dxi, right? So it's a sum over extensive displacement, things like volume change, charge change, times the conjugate intensive force. So the question is, can we write this here in terms of variables or properties of the system as well? And of course, that will bring in the entropy, right? This term, for those of you who will know, later will become TdS, and we will have to define S as a new property of the system. That's actually not the origin of entropy. The origin of entropy was a very practical one historically. It had to do with the conversion of heat to work, and it was, the second law was largely formalized by Carnot. Carnot, who was in the French army, following his family's footsteps, who were all French army officers. But he wasn't particularly interested in army operations. So he kind of got into doing science while he was an officer. And he essentially wrote a book on the second law because he understood that there were limits of conversion of heat to work. And it's kind of a fabulous book. It doesn't have a single equation in it, but it does have the statements of the second law. And there's a funny story about it that, you know, when Kelvin found out in England that Carnot had written a book about the second law, it wasn't exactly a bestseller. There was no internet. He couldn't get access to it. He spent several weeks in Paris trying to find the book, and actually went back home without the book. At least that's what he claims. Okay, so the reason there's a second law is because we have made some things implicit when we solve problems about the first law. But the other reason is that the first law, being an equality sign here, does not indicate directions of processes. So I made up a few silly processes that you can run in both directions according to the first law. So let's say you have a light bulb, right? And what happens to a light bulb? Well, electrical power goes in. Let's say this is my system boundary. And what comes out? Well, there's two things that come out, right? Heat and an energy flow that comes in as light. So I wrote it as EH nu. And what we know from the first law is that the electrical energy in has to be the heat coming out plus the radiation energy going out, right? Of course, there is nothing in the first law that states that you couldn't do this process in opposite direction, right? You could, in principle, make a light bulb that has heat going in, right? So heat going in picks up radiation and then has electrical power going out. And so the question is, we all know that that doesn't happen, right? Why is a process not allowed in that direction? The more trivial problem that you can think of is if you have two bodies at two different temperatures, call it T1 and T2 and T1. You know that heat can flow between them when T2 is greater than T1, right? But as long as the heat flow out of one body into the other body is the same, right? So as long as Q2 is equal minus Q1, energy is conserved. So in principle, you could flow heat from low to high temperature, according to the first law, right? So clearly the first law does not indicate proper directions of processes. And while these seem like silly examples, I want to show you some examples that regularly appear in the patent office as things that satisfy the first law of thermodynamics, but not what will become the second law. So let me share my screen here. Okay. Okay, the idea is to make the party boat here. The party boat takes in warm water. So here warm water comes in, and that brings with it some enthalpy, right? So I'll call that the enthalpy in. And the boat dumps ice, which we now know is at a lower enthalpy because it's at lower temperature, and it has also had the enthalpy of melting subtracted from it. So I'll call that the enthalpy out. And so in principle, this boat can produce work from that enthalpy extraction. And you can actually calculate how much that is. Let me do that math for you. So let's say we need a 1,000 horsepower boat. Right, a horsepower is 746 watts. So what I need is W needs to be minus 746 kilojoules per second. Right. So let's see how much ice I have to make for that. Right. So that means that the work has to be the enthalpy difference between the ice, so the enthalpy out, minus the enthalpy of the water coming in. And for simplicity, I'll both put them at the same temperature because this is mostly, the enthalpy change is mostly a result of the melting. So this is the mass of the specific enthalpy of ice minus the specific enthalpy of water. And this number here is minus 334 joules per gram. So what's my mass rate? So my mass rate of production is going to be minus 746,000 joules per second divided by minus 334 joules per gram. So it turns out that's 2.2 kilograms of ice per second. So if I make ice at about 2 kilograms per second, I could generate 1,000 horsepower. So there's a few things here odd. Well, first you could have a party on the boat, right? You could have a large cocktail bar that consumes 2 kilograms of ice per second. But besides that, what's kind of remarkable about this, right? Well, first of all, you know this isn't possible, right? Because if this were possible, we wouldn't have an energy crisis, right? We just take the warm oceans and turn them into colder oceans, and we generate a lot of energy. So clearly this is not possible. But the other thing you should notice is the scale issue, right? And we'll come back to this many, many times. 1,000 horsepower is a lot, right? I mean, you know, your average car is like 100, 200 horsepower. Small engines are a few horsepower. So 1,000 horsepower is a lot. And that corresponds to a relatively small mass, right? And we'll see this later again and again, that the sort of chemical energy content is so much higher than mechanical energy content. And you see that here already as well, right? Okay, so obviously you know that this doesn't work. And that's the origin of the second law. So the second law was essentially born out of observation that while energy needed to be conserved, there was clearly like not all energy was the same, and there was clearly a difference between heat and work. You could easily convert work to heat, but not the other way around. And so there's sort of several statements about the second law, which are in the slide notes historically, and I'll just read you a few. The Kelvin-Planck statement says that it's impossible to construct a process that operating in a cycle. Why is that there? That's because any machine that does the process should not be part of the change, right? Will produce no effect other than extraction of heat from a reservoir at one temperature and the performance of an equivalent amount of work. So basically this kills the party boat, right? Because the party boat was essentially extracting heat from the ocean at one temperature and trying to turn it into work. The Clausius statement says it's impossible to have a cyclic process with sole resultant heat flow from a cooler body to a warmer body. So basically Clausius simply says that you can't have heat flow from low temperature to high temperature, period. I mean, we'll show later that you can, but you need to do other things. And that's why Clausius said, whose sole result, right? It used to be sort of a hobby of people in thermodynamics to show the equivalence of all these statements, but we're not going to do that anymore. People have gone pretty mathematically on the second law. And the one that's actually kind of interesting is the Kara-Theodori statement, which you wouldn't recognize at first as a second law statement. It says that arbitrary close to any given thermodynamic state, there exist states which cannot be reached from it solely by means of adiabatic processes. You may wonder what that has to do with the second law, and I'm not going to go into that, but it's kind of an interesting mathematical statement, and Zemansky goes deeper into the equivalence of this with the conventional statements of the second law. So the statement that we will adopt in this class is a sort of more modern and probably now more common statement of the second law, which I want to write out even though it's in the notes. Let me unshare. There we go. So the second law has multiple parts to the statement. The second law proclaims the existence of a state function. A state function means a property, right? There's a property which is dependent on the state of the system, and it's referred to as the entropy. It's a function of all the extensive variables. And it monotonically increases with U. And for which holds that the change in entropy of a system is always greater than or equal to the heat flow into it across the boundary. So I write the text out because I want you to remember it, that we're all like scientists and we focus on equations, and this is what you will obviously remember always, right? That ds is greater than del q. But there's some other important things. The most important is here that S is a state function. So its integral is not path dependent. So if I know the end state, final state, end state, I know the entropy difference, right? It doesn't really matter what path I take. I'm telling you this now, but trust me, you will still get troubled by that on occasion. Okay, so that's the first important thing. And this monotonic increasing with U is essentially will, as we see later, will define the fact that temperature is positive, but it's slightly less important. Okay, so the An important point of the second law is that the second law gives direction to processes. And that's quite easy to say. Let me look at an infinitesimal path from a state 1 to a state 2. So these are infinitesimally separated. So if going from 1 to 2 is allowed, then the second law tells us that the entropy change as I go from 1 to 2 is greater than or equal to the heat flow along that path, 1 to 2, divided by the system temperature. And if the system temperature, if it's an infinitesimal path, then the system temperature remains constant. So my question is path 2 to 1 possible? Well, if you want to know if a process is possible, you just evaluate the second law for it, right? So you ask the question, is ds 2 to 1 greater than or equal to del q 2 to 1 divided by t, right? So that's the question we are asking. So let's evaluate that. I'll take equation star and I multiply by -1, right? So if I multiply that by -1, I get that minus ds from 1 to 2. If you multiply an inequality with a negative number, it switches the inequality, right? So it's less than or equal to minus del q from 1 to 2 divided by t. This is equal to ds from 2 to 1, right? And this is equal to del q from 2 to 1. So make sure you still see this, right? So what we have proven here, that in most scenarios, if a forward path is possible, so this is true, then this will not be true. The only time that you can take the path backward and forward is when the equality sign applies. So if you have a path where ds 1 to 2 is equal to del q over t, then the reverse path is possible too. Because when I multiply with -1, an equality sign doesn't change. But basically what we've proven here is that there is directionality to processes. So most paths are one-way streets. And sorry, I'm walking away from the board. I shouldn't do that, so you can write. And a path is reversible only when ds is equal to del q over t along the path. I feel like Vanna White pointing at the board here. Wheel of Fortune. Okay. I want to make a few notes about the second law. So first of all, the second law is a statement about processes, not systems. Most of the time when a system undergoes a change along an irreversible path, that doesn't mean I can't bring the system back to its original state. It just means I cannot bring the system back to its original state along the same path. So I'll give you a silly example. Let's say this is the ground and I have a mass here, and I drop that mass down and it sort of hits the ground. We will later, actually you could already now do this, prove that this is an irreversible path. And the reason is that essentially energy will get dissipated as heat. But that doesn't mean I can't bring the system back, right? So the system is now on the ground. I'll just lift it up and it's back, right? So the second law is a statement by processes, not about systems. So never say that a system is irreversible. It's the process that the system undergoes that is reversible or irreversible. Okay. So I know it's early in the morning, but now's the time to wake up, because if I'm going to say anything useful or anything that you should remember in this lecture, to think about, if you want to understand what entropy means, now's the moment. So drum roll. I feel like, Jen Young, I think the GSI should provide like music, like movie music and so. Can we get a drum roll? No, I see. Too complicated. So what I want to show you is that you too could have been Carnot. You could have come up with the second law, because the reasoning is remarkably simple. And I want you to understand it. Because it will tell you sort of what entropy is. And why the inequality sign. Because inequalities are strange in physics, right? You know, in physics, most laws have equality signs. You know, F is equal to ma, whatever, right? The Maxwell equations are full of equality signs. Nobody uses inequality. So why is there inequality? So previously, we defined two flows of energy, right? Q plus W is delta U. And what we're really now doing in the second law, so that was the first law, right? In the second law, we're making a distinction. The first law is all about saying that Q and W are the same. They both come with units of energy. The second law is all about saying that they're different. There's a distinction between flows. So what we are really saying is that if you add heat to a system, you make some weird property called the entropy go up by this amount. And this is for reversible. So why is there the greater than or equal sign in the second law? So the question is, why do we actually write it as ds is greater than or equal to del q? So why do we have this thing? Because, let me be a bit pedantic here, because what we're really saying here, right, if you have an inequality sign, is that ds is equal to del q over t plus something positive. And the something positive is the energy that's delivered under other forms but get dissipated as heat. Let Let me give you an example. I'll give you a minute.
Hi, Professor. Can you repeat one more time what you just wrote on the board? It's a little hard to read.
Okay.
Statement.
Here? Yeah. So this says something positive. And what this something positive is, it's the energy delivered under other forms, I should have said under other forms than heat, but get dissipated as heat. I'll give you an example of that that may clarify this. So let me take a system that I introduced to you before. Let's say I have a large block here. I'll call that A. And then I have something of like an infinitesimally small mass. So it's less important. And I rub this thing, so the top part, which I'll call B, I'll rub that back and forth over A, right? So it's like, say I take 2 blocks of wood and I rub them over each other. So there's friction here, right? As I rub them across each other. There are 2 viewpoints that I can take about that system to apply thermodynamics. I can say, well, you know, I'm smart. I know that this work that I'm doing, that actually generates heat, and the heat is going to go in block A. So perspective 1 is like, I've already put in some physics here. I know what's going on. So what's really happened to A is that heat goes in, right? And so I go like, and I know, once I know the amount of heat goes in, then ds is del Q over T for this system. But let me now take, maybe I'm not so smart and I really don't know that there's friction. So let me take view 2. So now I'm going to draw my system boundary differently. This is A, this is B, and I have work done across the boundary. Because now I draw my boundary here. So now the thing that transfers across the boundary is W. So now I have a problem, right? First of all, the boundaries that I draw should not change my physical solution. What happens to A is independent of how I look at the system. So here I said that the entropy goes up by an amount del Q over T, which is equal to, in this case, del W over T. But here, if I apply the second law, what can I write? I can write that ds is greater than or equal to del Q over T. And what's del Q here? What is the amount of heat flowing over the physical boundaries? It's 0, right? So this is 0. And do you now see why I need the inequality sign? Because these 2 statements are consistent with each other, right? Here I'm saying, you know, the entropy increases by an amount Q over T. Here I'm saying, I don't really know, but the entropy increases. So the 2 statements are consistent. And this is why the second law needs the inequality sign, because it is a macroscopic science, because it doesn't really know what's going on inside the system, right? So here, I was a smart ass. I kind of figured out what goes on inside the system. I know this really is all heat going in. I can figure it out. Here, I'm not so smart. Right? I just look at the system boundaries and I have no idea what happens to that work once it's in the system. It turns out it all gets dissipated. And because I don't know what happens to the work, I need this inequality sign. So in some sense, this something positive here, what is it really? It's the dissipated work, right? The work that got dissipated as heat. So the conclusion here is that the reason that the second law has the greater than or equal sign is that it needs to be applicable to any system definition. Including the ones that including the ones that have internal dissipation. I'm sorry, I know my handwriting is terrible, but imagine that you would sit in a classroom in the back seat and I was writing with chalk. Be even worse, okay? So this is really important, right? This is what will make you understand thermodynamics. There is no magic about all this stuff, you see? I mean, basically somebody said, yeah, ds is really del Q over T, but half of the time I can't figure out what del Q is. So it's gonna be greater than del Q over T, right? Okay? That's really the second law. Okay, let me do a few examples. And this seems like a big cop-out, right, for thermodynamics. But it's remarkable that with all this like ambiguity and generality, it's still useful. And I'm going to show you a few of those things, that there's still remarkable things that you can prove with it. So I'm going to start with an example of thermal equilibrium. By the way, did you never worry why you could do all these problems on the first law without having the second law? Do you ever worry about that? It's because we influenced you indirectly, right? We plant stuff in your brain. So like when you solve problems with a tank, gas going in, gas going out, you assumed that equilibrium is determined when the pressure inside and outside is equal. You were already building that in, but we actually never proved that, right? When you did heat flow problems or something, right, in the first law, you know that the equilibrium is when the temperature outside and inside is equal. Let's say when you have a diathermal wall, but we never proved that to you, right? So the only way you could really solve the first law problems was by using kind of assumptions that you intuitively know are correct, but we actually never proved them. The second law will prove them, right? So the first one that's I want to prove, which is kind of easy, is thermal equilibrium. And then later in the next few lectures, we'll do a bunch more general equilibrium. So let's say again, I have two bodies at different temperature. I'll call them T1, T2, and I'm going to put a heat conductor between them. And for the sake of argument, for simplicity, I'm going to assume that the heat conductor is a perfect conductor, but has zero mass. The reason is I don't want to count the conductor as part of the system that takes up heat, right? It doesn't actually have to be a perfect conductor, you just have to have zero mass. Okay, so through the conductor here, there's some amount of heat going in delta Q1, there's some amount of heat going in delta Q2. And of course, if the whole system is insulated, is made adiabatic from the environment, then the first law tells us that del Q1 has to equal minus del Q2, right? Energy has to be conserved within the system. So, okay. So how do I know which direction the heat flows? So let me apply the second law. So for that, I have to calculate the total entropy of the system. Which is just the sum of the entropy change. The entropy of the total system is the sum of the entropy changes of the individual systems. What do you know about ds total? I feel like we should have numbers in class and then we randomly pick numbers. Then nobody has to volunteer. What do you know about ds total? Well, the total system is isolated from the environment, so there's no heat flow into the system. So this has to be greater than or equal to 0, right? Okay, so we can now write ds total in terms of the heat flow, because we know the heat flow in each of the subsystems. So ds total is equal to del Q1 over T1. That's ds1 plus del Q2 over T2, which, if I use the substitution of the first law, this is del Q1 times 1 over T1 minus 1 over T2, which is del Q1 times T2 minus T1, T1, T2. So this has to be positive. So what does that mean? If T2 is greater than T1, then this term is positive. So this term has to be positive. Then del Q1 has to be positive. If T2 is less than T1, then this term is negative, so this term has to be negative. So then del Q1 has to be negative. So what have we just proven? Well, if T2 is greater than T1, so this is higher temperature, then del Q1 is positive. So that means del Q2 is negative. So heat flows out of 2 into 1. So we've just proven that heat flows from low to high temperature, right? Which is basically the Kelvin-Planck statement, or sorry, the Clausius statement. I have a question for you, and this one I need an answer to, or I'm not moving on. I'm striking. So let's say that there is a temperature differential. Like, I don't know, T2 is 100 degrees higher than T1, say, right? So then this is definitely a finite quantity, T2 minus T1. So that means the entropy increase is real. There's a real entropy increase. So ds is going to be greater than 0 when I have heat flow. So this system is irreversible. Sorry, I already made my own mistake. The process the system undergoes is irreversible, right? There we see that if I flow heat from the high temperature to the low temperature, and they are different by a finite amount, then ds is positive, meaning that heat flow process is irreversible. But something puzzles me here. When I looked at ds1, right, I wrote it as del Q1 over T. I've assumed reversibility for the heat flowing in 1. The same for the heat flowing out of 2. So I have 2 reversible events put together in a system, but the system is undergoing an irreversible process. So where is the irreversibility here? Somebody needs to answer that, or I'm quitting. I'm taking off early today. Where is the irreversibility? I see we're thinned out. Only the strong survive. Where is the entropy being generated, right? It's obviously not in system 1 and in system 2, because I've kind of assumed that this is reversible here. So somebody wants to answer this? Just give it a shot. Hey, what else is there if it's not in 1 and 2?
Is it in the lossy transfer?
Yeah, yeah. It's in this gradient here, right? Because there has to be a gradient in temperature somewhere, right? Because this is high, this is low. I really don't know where that gradient is. It could be in the bar, it could be in the interface, right? If you solve heat transfer problems, you'll figure it out. But somewhere, the energy is cascading down in temperature, right? This heat flow is coming from high temperature to low temperature, is cascading over a temperature gradient, and that's where the entropy is being produced. Because if you look at it, right, why do we generate entropy? It's because we flow energy between two different temperatures. If we move energy between the same temperatures, assuming you could do that, you could kind of do that infinitesimally slow, you don't produce entropy. It's because you cascade it across a gradient. And the reason I'm bringing this up, because this is a general idea in thermodynamics. If you transfer an extensive quantity over a gradient of the intensive quantity, you will always generate entropy, right? So if you expand volume in a gradient of pressure, you will never be reversible. You will degenerate some work into heat and be producing entropy. As we do more real material science problems later, you will have this when you have concentration diffusion, right? If I start with a region, let's say I have an alloy of A and B, and I start with a lot of B on the surface and I diffuse it in, I'm diffusing it along a gradient, I will be generating entropy, right? It's only when you diffuse or move an extensive quantity across homogeneous intensive variables, right, that you actually can be reversible and not produce entropy. Which is, by the way, also why reversible processes can only be done infinitesimally slowly. But more on that later, okay? I'm just giving you a look forward. It's like a TV series, right? Coming up. Which I hate when they do that in a TV series. Who wants to see what's actually coming up? I mean, like, it sort of spoils the fun. Anyway. Okay, a few comments regarding entropy. Entropy is not conserved. So the fact that it's a state property does not make it a conserved quantity. For example, this example that I did of rubbing two blocks against each other, right? I put work into the system and I make the entropy of the system go up. But the entropy of, there's nothing else that has gone down because work is being transferred from the environment, not heat. So nothing went down in entropy here. So entropy is definitely not a conserved quantity. Two, the entropy of adiabatic systems always increases. And that's kind of obvious, right? Because the S is greater than or equal to del Q over T, and this is equal to 0, so it's greater than or equal to 0. So if you isolate a system from the environment in terms of its heat flow, okay, the entropy always goes up. So people have pushed this to the limit, right? If I take the universe, we could have a debate of whether the universe is isolated, but the entropy of the universe always increases. And that's why sometimes entropy is called the arrow of time, which is very poetic, but because sadly, entropy means that we're only going one way in the universe, right? There is an endpoint to the universe when the entropy is maximal, as we'll see. And this is kind of hard to believe because if you think about it deeply, almost all the mechanical equations we know, quantum mechanics, Newtonian mechanics, all these are time reversible. So forget about quantum mechanics for a second, but you know, most of the world behaves Newtonian. So you could actually just invert everything in Newton's equations and we should all be going backward. And so Newtonian mechanics is incompatible or seemingly incompatible with thermodynamics. This is a subtle paradox that we're not going to spend that much time on in class, and a lot of people have spent time on it. It turns out the two are compatible, but it has something to do with the probability of initial conditions. And you can read a little more about this when you do stat mech, but it's kind of remarkable, right? All our fundamental equations, atomistic equations, are time reversible. But thermodynamics is not. So there's something that happens when you do macroscopic averaging where you lose reversibility. Okay, and I fear I'm being way too simplistic here, but I'll write it down since I've learned the hard way from the typical errors are made. Entropy of systems can of course go down, right? Sometimes I see on exams people write, oh, entropy always goes up. That's only for adiabatic systems, right? If I take a system and I cool it by extracting heat, obviously the entropy of that thing is going down, right? It's just that the entropy of something else has to be going up even more. So the total entropy of the universe goes up. Okay. Time for coffee. There are really cool things you can prove with the second law. And I want to just prove a few. So I want to prove a few consequences of the second law. Those were comments, these are consequences. I guess consequences are more complicated than comments. Okay, the first one is that if you take a reversible or an irreversible path between two states, the work along the reversible path is always less than the work along the irreversible path. I'll prove that in a second. Actually, I'll prove it now. Here we go. So what I'm going to do is I'm going to take an infinitesimal path between two states again. And I'm going to take a reversible path. And then I'm also going to take bad pen. This is the season. Okay, and then I'm also going to take an irreversible path, right? But I'm going between the same two states. So I'm going to write down the first and second law for these paths. So for the reversible path, I have that du of the system. I'm just going to write R and I, R for reversible, I for irreversible. So is the heat flow along the reversible path plus the work along the reversible path along the irreversible, I can do the same. du system is equal to del Q irreversible plus del W irreversible, right? And of course, these have to be the same because energy is a state function, so its change is independent of path. So these two here have to be the same. Okay. So let me write that out. Del Q reversible plus del W reversible has to equal del Q irreversible plus del W irreversible. I can apply the second law here. This is equal to TdS because it's a reversible path. And along the irreversible path, this is less than or equal to TdS, right? Because this is the irreversible path. So I can now eliminate TdS from this equation. And what I find is that del W reversible is less than or equal to del W irreversible. So if you were living in the, well, in any century, this is kind of an important statement, right? But you can kind of see why people in the 19th century were so go-hung on the second law. Because the Industrial Revolution was all about using work and getting work, right? So let's say you make a machine that produces work. So that means that W is negative, right? Coming out of your system. So what we're saying here is that in the reversible case, it's less than the irreversible case, so it's more negative. So if I have a machine that produces work, if I do it in a reversible path, I'm going to produce a lot more. Even though I take the same cycle, I go between the same path. If on the other hand, let's say I build a compressor, something that I have to put work in, right? So the work is positive. So now this is saying that the reversible work I have to put in is less than the irreversible work, okay? So basically, reversible processes are more efficient, right? Given that we tend to care about work a lot more than we care about heat. So this coincides with your intuition that any form of irreversibility is kind of wasteful. That's essentially what we're proving here, right? So the second important thing, and I apologize for you mechanical engineers, you're going to have seen all this before, is that there are limits in conversion of heat to work. There are limits of heat to work conversion. Which is essentially, let me prove the Kelvin-Planck statement. Right, the Kelvin-Planck statement said that essentially, if I do some process in a cycle, I cannot, if I only bring in heat from one temperature, I cannot generate work. So let's prove that. Well, I want to do this process reversible because I want to be most efficient, right? That's going to produce the most work. Okay, that means that for a reversible process, I can calculate the entropy generation in a cycle. Well, that's the integral of del Q over T. And that has to be 0, right? Because the entropy is a state function. So whenever I come back into the same point, the entropy change of the system is 0. So if only one temperature, so temperature is constant, that means that Q has to be equal to 0. right? Because if temperature is constant, I can take it out of the integral, right? So then the integral del Q is 0. So what does the first law tells me? Well, the first law tells me that delta U is W plus Q, and because delta U is a state function, it's also 0 in a loop, is 0, but now Q is 0, so that means W is 0. So everything is 0. Terrible. So basically, what the second law tells you, and which Kelvin Planck already told you, that the best you can do in this scenario is do nothing. The best you can do is have a cyclic process in which no heat comes in, and therefore, because of energy conservation, no work comes out. Okay? So how do you solve this problem? Let your engineering neurons fire, right? You figure out where does the problem fundamentally come from, right? That's where you're going to attack it. And the problem fundamentally comes from this constraint here, right? That the entropy of my system cannot change. That's not something I can fix because my machine cannot change. But that's the integral of del Q over T. And if I have only one T, then Q has to be 0. So I can't put any heat in. So if I had a temperature distribution, then I can make this integral 0, but the integral of del Q would not be 0. So the easiest temperature distribution is to take two temperatures, right? And I'll call them T high and T low. So if I have two temperatures, then delta S is now, well, I have a certain amount exchanged at the high temperature, and I have a certain amount of exchanged at the low temperature, right? This still has to be 0, but now the sum of QH plus QL doesn't have to be 0, right? So the second law now only imposes a relation between QH and Q low. So Q low is minus T low over TH times QH. So what's the work that I get out? So I just have, for that, I just have to write down an energy balance. So W is delta U. And again, for a steady state system, that's 0 minus QH minus QL. So if I substitute this all in, I get minus 1 minus TL over TH times QH. And this is really cool, right? We've beaten the second law. Totally. We've cheated the second law by doing heat exchange at different temperatures in just the right balance so that the entropy is conserved. And that allows us to get net heat into the system, and that means I can get work out. So the sort of process diagram of this is that you have some machine where you put heat in, where you have some high temperature reservoir and you flow heat in, and then you reject that to some low temperature reservoir, and then work comes out. Now, I've assumed here signs that I kind of know what the signs are of these flows. And one way you can kind of figure this out, right? Let's say I want a machine that produces work. So that means W is negative. There's a minus sign here. This term here is positive, so QH has to be positive, right? If W is negative, if I want W to be negative, then QH has to be positive. So what that's telling me is that the only way I can produce work out of heat is by making heat come from a high temperature, reject it at a low temperature, and the balance of the two is W, is the work that I get out. So we finally made our work producing machine. And again, you can see how people would have been tremendously interested in this historically, right? So this is a reversible process, right? I've assumed that here. So if this is a reversible process, then this is the best I can do. So what I've shown you here is that if I have two reservoirs with which I can exchange heat, the best work production I can do is what's written down there. So we can define the efficiency and how do you define efficiency? What's the time? Okay, some time. How do you define efficiency? Well, efficiency is always what you pay, what you get divided by what you pay for, right? Like if you ever worry how to define efficiency, if you have any business sense, that's what it is, right? What do you want? You want minus W, right? That's what people pay you money for. And if you run a power plant, what do you pay for? The heat at the high temperature, right? So that's your efficiency, right? This is what you want. This is what you pay for. So that is equal to 1 minus T low over T high. And this is what's referred to as the Carnot limit. The Carnot limit says that the conversion of heat to work is limited by the temperatures between which you can transfer that heat. So let's put in a few numbers for Carnot temperatures. So let's do example. Let's say the high temperature is just boiling water. So let's say TH is 100 C and T low is room temperature, like 25 C. Right? So then efficiency equals 1 minus, and you have to put the temperatures in Kelvin, right? 1 minus 298 divided by 373, and that's 20%. You know, it's kind of yucky, right? Because, so basically, all the stuff you do at high temperature, that's like fuels you have to burn, right? Nuclear reactors, whatever. You're only getting 20% out as work. So a power plant that runs between 100 C and room temperature is pretty much just a heat degeneration engine, right? You burn stuff, most of it comes out the back end as cooling, and only a little bit comes out of work. So what do we have to do to make this better? You have to get this efficiency up, right? So you have to get this number here close to 1. Sorry, close to 0. So how do you do that? Well, you can't really mess with T low. You only have so much control about where you can dump heat. You can't make something cold to dump heat. So you make TH really high. So let's go high. So let's say TH is 550 C, like a typical modern boiler. T low is 25 C. So now the efficiency is 1 minus 298 divided by 823 Kelvin. So this is 63%. So already much better, right? So if we can run the high temperature operation at 500 Celsius, 550 Celsius, our best efficiency we can do is about 60%. So if you go higher, you can do even better, right? But what stops us from going higher? It's the ability to do this high temperature process, right? Let's say, you know, I want to do 1,000 degrees. So I have to find an instrument or an operation where I can deliver heat at 1,000 degrees and then run a power plant with. And so typically the heat delivery is done in a boiler. You can boil easily water at 100 C. You can boil at a few hundred degrees by putting it under pressure, right? You can raise the boiling point of water. But if you go to 1,000 C, you have all kinds of problems, right? Temperature is super high. The metals have to withstand very high temperature, and the pressure is really high, right? If you were to try boiling water at 1,000 C. So raising this temperature to higher is really hard. Now I'll tell you that if you were limited to 60%, and by the way, then you have some real inefficiencies in the system, so this gets degenerated down to like 55% or so. But modern power plants can do better. Modern power plants now can hit 60% real efficiency, which means the theoretical efficiency has to be much higher. Jet engines do much better. So how do they do it? I mean, you're the engineers, right? You got to figure this out. How do you do it? How do you go even higher temperature? Because the higher temperature you do the combustion, right? If you can put this at 2000 degrees, you're golden, right? You can calculate this. Once you hit 2000 degrees, this efficiency starts to hit like, you know, close to 1, right? How do you do it? How does a modern jet engine fly? Can I tell you, like a jet fighter, like an F-35, would not be able to take off at 60% efficiency. It would have to carry so much fuel that its takeoff weight would be too high for it to take off. So how do they do it? You're the engineers, right? I'm just teaching you thermal. How do they do it? Okay.
Does pressure change things?
Yeah, not really. They don't mess too much with pressure. How does a jet engine work? There's no boiling of water or anything, right? You just make a flame. The flame gets really hot. So what they do is they essentially make the flame so hot, but they never make it touch any material. So basically the flame in a jet engine is sort of confined to the center and never touches the walls. And the walls are actually cooled. They have cooling in it. So inside the combustion area, you are much higher than any temperature the material ever sees. On top of that, they use super high strength materials like nickel, aluminum, super alloys that can withstand high temperature. But the core temperature of the flame is so controlled that it never touches the wall. So they can reach super high efficiency. And that's where a lot of efficiency gains have been in engine technology. And that's been transferred to power plants, right? Some of you may have heard things like what are called combined cycle power plants are essentially a jet engine that then its waste heat gets turned into a Carnot engine, if I can simplify that. So again, the first combustion you do doesn't touch any material. You'll touch some fan and some. What happens when I reverse this machine? Because we said it's reversible. So if I reverse it, sorry, I need a different color. Let's do pink. Okay. If I reverse it, W goes in, QH goes this way, and Q low goes that way. What did I just make? I made a refrigerator, right? What's a refrigerator? It's a device that pumps up heat from a low temperature that's inside your refrigerator, and it dumps it into your room. And it uses electricity, so it gets a W input to do that. So I used to ask these questions when I was at MIT on PhD exams, if your room is hot, should you open the refrigerator? The answer is no, right? I mean, you get some really temporary relief, right? When you stand in front of the refrigerator, but the refrigerator is nothing but a heat pump that pumps up heat from the inside of the refrigerator and dumps it on the outside. Now, an air conditioner is smarter, right? An air conditioner is a refrigerator, but it dumps the heat on the outside, right? An air conditioner pumps heat from the inside of your house to the outside because the condenser that releases the heat is outside the house. So you could turn your refrigerator into an air conditioner. If you position it, you stick it in the window, you open the door, and the cooling coils on the back sit outside your window. right? Then you would turn your refrigerator into an air conditioner, which this weekend may have been useful knowledge. So I should have given you this lecture before. Okay, so one more thing before we have to end. What else is it? So if I am interested in Q low, then it's a refrigerator. But what if I'm interested in QH? Then it's what's called a heat pump, right? So if I now put Q low outside the house and QH inside the house, so then I'm pumping heat from outside to inside. So if you live in a cold climate, that's great, right? Because I can heat my house by pumping heat from the outside to the inside. So the question is, what's the efficiency of that? So let's do a heat pump. Okay. So how would you define efficiency? How would you define efficiency of a heat pump? Remember I told you it's what you want minus what you pay for. So what do you want? You want heat to, at high temperature to come out of the heat pump. So you want it to be negative. So it's minus QH. And what you pay for is W. So when you figure this out, when you put in all the equations that I use there, you can prove that this is equal to TH divided by TH minus T low. Obviously, you can already see this number can be larger than 1, right? So let me put in some numbers. If TH is 25 Celsius, so it's the inside of your house, and T low is the outside, and let's say it's just freezing, so 0 Celsius, then TH over TH minus T low is 298 Kelvin divided by 25 Kelvin. So it's 11.9. And again, this is defined as minus QH over W. This is amazing, right? So what I'm really telling you here is that for 1 watt of electricity, I can generate 12 watts of heat in my house. Now in reality, it's a little less, right? These limits are not very realistic. To actually have reasonable heat flow, I would have to pump up to like 40, or because you need some kind of heat gradient, right, to get the heat. This is probably a little lower too. But in reality, these things still have like what they call coefficients of performance of 3 or 4. So how does that compare to an electric heater? Like one of these things that I buy at Sears when they still existed. Like what's the conversion efficiency of an electric heater?
Isn't it max 100?
Yeah, it's always 100. Thank you. Because in electric heater, I convert all electricity to heat. And I used to have an ad, I think I put this on an exam question once. Sears used to advertise efficient electric space heater. That's like the dumbest thing ever, right? They are perfectly efficient by definition. All the heat gets dissipated in a resistor, all the work gets dissipated in a resistor and comes out as heat. Every space heater is 100% efficient. Because otherwise the second law of thermodynamics wouldn't apply, the first law of thermodynamics wouldn't apply. But what I'm telling you is you can do much better. If you buy yourself a heat pump, you can get 12 joules of heat for every watt. So in reality, coefficients of performance, as they're called, so in reality, in real systems that you buy, this tends to be 3 to 4. This efficiency. But that's still amazing, right? It's still so much better than a pure electric heater. So how much time do I have? I have 5 minutes. Perfect. You know, since we all care about climate and environment, and I want to show you some interesting math. That this is a new part of the course. It's only been there for a year because I didn't know this until somebody else told me. So I want to do the same math for you. So should you heat your house with electricity and a heat pump or with natural gas? Right? And you know, in California, you may not care so much because you almost never have to heat your house, but in most of the US, you do care. So let me do the two scenarios. Okay, if I burn natural gas, right? That's CH4 mostly, right? Natural gas. What do I get? Well, assuming my boiler and everything is, my furnace is highly efficient, so what I get is the delta H, right? That's the heat that I put in my house, assuming I have no losses. A typical furnace, a really good furnace is 96% efficient, but then you have some losses in the ductwork. So I'll set it to Q, but it's probably more like 0.9 Q. So the heat to the house is delta H of the reaction. Okay, so now I'm going to do another scenario. I'm going to use the natural gas in a power plant, which makes electricity. And then the power plant, that electricity is going to run a heat pump in my house. Okay, so now I'm going to, the gas is going to make electricity. And that's going to drive a heat pump in my house. Okay, so the electric work that I get out is the efficiency of the power plant. So I've written PP is the efficiency of the power plant times delta H, right? That's my heat of combustion of the gas. And the heat I get into the house is the coefficient of performance. So this thing is actually called the COP, sorry, which stands for coefficient of performance. So it's what's called the COP or COP times the electric work I use, right? So I'm going to make some low ball estimates here, right? If I set this to like some pretty low number for a modern power plant, so I'm going to take sort of a low ball estimate. Let's say I set this to 0.4, so 40%. And I set this to a low ball estimate of 3, but it's typically between 3 and 4. What you see is that Q house is 1.2 times delta H. So even in my very low ball estimate, I am more efficient by using an electric heat pump to heat my house. Now, in the better, right? So this can easily go up to 0.5 and actually higher now. This can be 4. If this is 0.5 and this is 4, then this is 2. So in a more realistic scenario, I really shouldn't be using natural gas to heat a house. I should be making electricity with the natural gas, and I should be using a heat pump in the house. And this was not true 30 years ago, which is probably why I didn't know it, since I'm that old. Because electricity generation was not that great, heat pumps were not that great, but today it's true. And so from a CO2 perspective, making electricity and using heat pumps is a better deal than just burning natural gas in your house. And there's another part to the equation, right? If your electricity comes from solar, which a lot of our electricity in California does, then there is no CO2 generation, right? Then I have a highly efficient way because there's no combustion that generates my delta H. So if my electricity input is from solar, I have perfect heating with no CO2, right? And that's why now in modern building technology, if you want to be like platinum LEED certified and so, this kind of stuff starts to play a real role. And people are building more and more heat pump systems. The other thing about heat pump system is that they can be much more localized than natural gas furnaces. Modern cars have heat pumps in them. So modern cars that have part electric drive, like PHEVs and EVs, the first generation had simply electric heaters, which is dumb, right? But because you want to really conserve the electricity stored in the car, if you buy a modern EV, they actually have heat pumps that heat the car. They're not heated by resistive heating. Okay, perfectly on time. Cool. I'm done with that. If you have, I'm sorry, I don't have time for questions since, like I said, somebody else. But if you have questions about this, just ask me on Friday. Right, Friday's a class. There we go. I'll see you on Friday. Enjoy the rest of your day. Cool. See you later. Bye.